Another fun and exciting thing we're going to be doing in this week is graphing, not graphing. Well, we are graphing that too, but solving rational and polynomial inequalities. So some guidelines to keep things nice and organized is first thing to do is make one side of the inequality 0. So a lot of times it'll just already have one side equals 0, but sometimes you might have to move some stuff around. The next thing to do is to factor. Find your boundary points. Now, boundary points, I think we've called them cut points too. That's where your denominator is going to be 0 or the function is equal to 0. So if it's a rational, you have a numerator and denominator, top and the bottom, so that'd be where the top and the bottom is equal to 0. If it's just a polynomial, it's just where the polynomial is equal to 0. After you've done that, then you're going to make an interval with your boundary points or your cut points and test in each of those intervals. Now, if you have like a TI 83 or something, or 84 or whatever you're using in the AIM course, you can use the table to kind of expedite this process. Alright, so we'll look at one. We got some polynomial function. I know it's a polynomial because it's we're only doing rational or polynomial, and this is not rational. So we have x minus 5 times x plus 2 quantity squared, and that's going to be greater than 0 in this example. So I'm going to set each factor equal to 0. Notice that the x plus 2 has multiplicity 2, so that means we're going to bounce or touch, so it's not going to change signs at 2. Or not 2, but negative 2. If we solve both of those, we get x is 5 or x is negative 2. Those are my cut or boundary points. I'm going to go ahead and put them in. And then what I like to do, just so I figure out what the intervals are before I jump into finding the doing the test points, is I like to write in my intervals. So we have negative 2 to negative infinity to negative 2, negative 2 to 5, and 5 to infinity. Those are my 3 intervals, and I'm going to need to test in each one. So I'm going to go ahead and test in the original inequality. So we'll test something in the interval negative infinity to negative 2, and that'll be negative 3. So we're just going to replace the x's with negative 3, and then I'm looking for, is it true or false? So we go ahead and plug that in and crunch some numbers, and we get negative 8 after we do all that. And we were interested in, when is it greater than 0? Well, negative 8 is not greater than 0, so that's going to be false. So if you like, you can cross out that interval. We're not going to use it. Now we'll move on to the next interval. We'll test something in the interval negative 2 to 5. How about 0? So go in and plug it in, crunch the numbers. Negative 5 times 2. And that's also going to be false. And remember I said that x plus 2, that had multiplicity 2, so that meant we were just going to bounce or touch at negative 2. So we got both false on either side, so we got negative and negative, so that's fine. Now we'll test something in the interval 5 to infinity, so 6 would probably be nice. Plug it in, work it out, and we get 64 this time, so that's true. So the only interval that worked was 5 to infinity, and then I'll go ahead and graph it in. We knew it was negative down here, and we knew it was just going to touch at negative 2 and then cross at 5. Okay. Alright, moving on, I got another example of a polynomial. So let's see. Good thing is it's already one side 0. We're going to try to factor this. The GCF, it looks like, is going to be an x, so we're going to factor an x out. And then we're going to go ahead and factor the remaining piece, the x squared minus 2x minus 8. So we're going to need a product of negative 8 and a sum of negative 2. So our factors are going to be negative 4 and positive 2. Notice all of these have multiplicity 1, so we're going to be crossing at each one of these cut points or boundary values or critical numbers, however we've called them in class. And notice I've also set it equal to 0. That's just to kind of facilitate solving this. When we actually start doing our testing, we'll go back to the inequality. So if we set each factor equal to 0, we'll have x is 0, x is 4, and x is negative 2. So I call boundary points, or maybe cut points is what we've also called them. So we'll go ahead and draw our number line in with our 3 boundary points. And we'll write in our intervals also for each one. So we don't have to go back and write in what those intervals are later on. We'll have them there ready to go. In the first interval, negative infinity to negative 2, why don't we pick negative 3? And we'll go ahead and plug it into the original inequality. Careful with the parentheses, especially if you're using a calculator, because it's really easy to make a mistake here. If you're using the table on a more sophisticated calculator, you won't have to worry about this. So work that all out, and we get a negative, and we are interested in this thing being positive. So greater than 0 would be positive, so it's false there. We're going to cross out that interval because it doesn't work. Then pick something in the next interval, negative 2 to 0. And it should be positive because I said everything has multiplicity 1, so we should be doing something like this. Negative to positive, down negative to positive. So it should look something like that because everything's multiplicity 1, so that means we're going to cross. So plugging negative 1 in and being careful about the signs, we get a positive 5, and that's true, so you can put a check mark or something on that interval to indicate that, okay, that one's good. Now, if we move on to the next interval, 0 to 4, a nice number to pick would be 1. We'll go ahead and plug it in. And we get another negative, so that looks good from what we just said. That's going to be false, so we're going to cross out that interval. Remember, we wanted to be positive. And lastly, we'll pick something in the last interval like 5. And again, be careful plugging the numbers in. And we get true. And we get 35 is greater than 0. So my solution is going to be the union of these two intervals that were true. Go ahead and write our solution. Negative 2 to 0, union 4 to infinity. And then we can go ahead and draw on the graph. So we started negative and we crossed at each one of our cut points or critical points, boundary points, whatever we want to call them. Okay. So these two were examples of polynomials, and we'll do two with rationals. So remember with the rationals, we needed to set the numerator and the denominator equal to 0. So for this particular one, we want this rational to be greater than or equal to 0, so we're looking for positives. So set both the numerator and denominator equal to 0. Those are going to be our boundary points or cut points. Okay. Now we got to be a little bit careful about this. We got the greater than or equal to there, and a lot of times that means that we can use brackets. However, we cannot use brackets involving negative 2. And the reason why is because if we plug negative 2 into the denominator here, we're going to end up dividing by 0, and then it's going to explode YouTube and your computer. So we don't want that to happen, so we're going to use parentheses at negative 2. However, at the 4 is okay. That's going to make the numerator 0, and we're allowed to equal 0. So we're okay with putting brackets at 4. So let's go ahead and draw in boundary numbers, critical points, and write in our intervals. And I just said it, but then I didn't do it. You can put brackets at the 4s, that's fine. I think I do later in the video, but you can put brackets at the 4s. Okay, so we'll pick a test value in the first interval, plug it in. We're looking for, is it positive? We got negative divided by negative, which is positive, so that's a good interval. Then we'll pick something in the next interval between -2 and 4, so 0 sounds good. 0 is nice and easy to check. And we get a negative, so that one's false. We're going to cross that interval out. And finally, we're going to test something in 4 to infinity, so maybe 5 is a nice one to test. Alright, so we have another true, so our solution's got to be the union of the two true pieces. Okay, so pretty straightforward. It's a lot like the polynomials. You're picking your test points. The only thing you got to fuss with is the denominator being 0. That's the only thing you need to be careful about. -2 could not have a bracket on it because we can't divide by 0. Alright, let's do one more. We're going to look at one that's a little bit trickier because it's not it is not greater than or equal to 0. So we're going to have to do a little bit of trickery here to get it to equal to 0. So we'll subtract 1 from both sides, and then we have to be clever about what we're going to do here. The common denominator is 2x plus 4, so a flavor of 1 would be 2x plus 4 divided by 2x plus 4. So x minus 4, and then here's the subtracting 1. This part right here, that's subtracting 1. We can go ahead and simplify this, and then it turns into a lot like the previous problem. We need to set the numerator and denominator equal to 0. X minus 8, negative x minus 8 is going to be equal to 0 when x is -8. And then in the previous example, we had the same denominator, and that was equal to 0 at -2. Again, we can't put brackets at -2 because we do not want to divide by 0. However, at the -8, that's perfectly fine. We can go ahead and put brackets at the -8 because if the numerator is equal to 0, that's all right. We're allowed to be equal to 0, so we're fine there. Okay, now it's the same process as before. We're going to pick our test points, and we're looking for positive or negative. I'm sorry, a little bit different. If I'm testing in the original, it needs to be greater than 1. The original said greater than 1. So if we plug in that first one, we get 5 over 22, and 5 over 22 is not bigger than 1. So we're looking for larger than 1. Sorry about that. Okay. If we use -3 as a test point, we get 7 halves, and 7 halves is greater than 1. I think it's 3.5, so 3.5 is bigger than 1, so that's going to be true. And then we'll pick something in the last test interval, and we get a negative. So our solution's just going to be the interval that was true. Okay. So the hardest part is finding that common denominator right here. That was kind of probably the most difficult part there.